Another hello from West Virginia. Clearly not. Okay, but what I clearly do have is joke of the day, and I know you're ready for it. So my uncle was in the Navy, and he got lost at sea. He was learning Morse code, and he did all right with A and B, but he kept getting lost at sea. Lost at sea. Okay, anyways, what we are not going to be lost on is combining like radicals. Now remember, you know how to combine up like terms. You know that when you have a 5x plus a 3x, you know that they are alike because they both have x to the first power. And when they are alike, it's kind of like saying I have 5, literally, of the letter x, 5 of them in the pile in front of me. I'm going to put 3 more of those x's in the pile in front of me. How many x's do I have? I have 8 of them. And notice what happened here was we kept what was making them alike. The variable was what was making them alike. We did not add these up and get an x squared. We only did what I call work the coefficients. So we retained what was making them alike and we worked the coefficients. A similar idea can happen when you have radicals. You can add or subtract like radicals. Again, they have to be alike. So in other words, what's going to make them alike is the radical itself. As you look at these examples, and I'm going to add or subtract them, notice this says 9 square root of 3 plus 8 square root of 3. Now what you need to understand, let's go back to this one. When I had 5x and they were sitting up against each other, and sitting up against means multiplication, I have said many, many times that the word of means multiplication in math. So if this is multiplication, it means I have 5 of the x's, and I have 3 more of the x's. So down here, when I have 9 square root of 3, that means I have 9 of these square roots of 3. The square root of 3 actually represents a decimal number, and so what this is saying, I have 9 of those crazy decimal numbers. And I'm going to add 8 more of those crazy decimal numbers. So it's kind of like saying I have 9x plus 8x. I have 9 of those square roots of 3 and 8 more of those square roots of 3. So just like here, we would combine that, we'd work those coefficients, and we would keep the variable and get a 17x. Same thing's going to happen here. If I have 9 of these square roots of 3 and I throw 8 more of those square roots of 3 in the pile, how many of those square roots of 3 do I have? I have 17 of those square roots of 3. So once again, I'm going to retain what's making them alike. The variable, or in this case, the radical is what's making them alike, and I'm going to work those coefficients. Now, take a look at this one. I have 2 of these square roots of 3. I'm taking out 3 of them. I just went, not square root of 3, I'm so sorry. I have 2 of these square roots of 11. I'm taking out 3 of these square roots of 11. I just went in the hole how many of them? Yes, I went in the hole 1 of those square roots of 11. Now I'm going to take that negative square root of 11. I'm going to subtract 6 square root of 11. So I just went in the hole 1. I go in the hole 6 more. I am now in the hole how much? I am in the hole negative 7 of these square roots of 11. Because again, 2 of the square roots of 11 minus 3 of the square roots of 11. So once again, what I'm going to do here, and negative 1 of these square roots of 11 minus 6 of these square roots of 11. I'm going to work those coefficients. I'm going to retain what's making them alike. The radicals are what's making them alike. So now let's take a look at one more, and then we'll just kind of shake things up a little bit. We've got 6 of these square roots of 5. Again, sitting beside means multiplication, so I have 6 of those square roots of 5 plus 1 of those square roots of 5. So when I work those coefficients and retain those radicals, because that's what's making them alike, 6 and 1 will give me 7 of these square roots of 5. But I'm going to take these 7 square roots of 5, I'm going to take out 7 of those square roots of 5. So if I had 7 of them and I just took all 7 of them out, how many do I have? I have none of those square roots of 5. Or you can look at it and you can say, I really just don't have anything at all. Because yet again, these are sitting beside each other. Sitting beside indicates multiplication. 0 times anything at all is going to be a 0. Now, let's shake it up just a little bit, because sometimes you're not going to have like radicals. And when you don't have like radicals, then what are you going to do? Take a look at this one. This says I have 5 of these square roots of 27, and I'm taking out 4 of these square roots of 3. But the problem is, I don't have any square roots of 3 in there. I only have square roots of 27. Now what am I going to do? Well, sometimes you might need to simplify that radical in order to make them alike, because we've worked with simplifying radicals. We can simplify square root of 27 because remember, what we're looking for is perfect squares and pairs. Can you think of a number that you can multiply by itself to create a 27? Nope, and I can't either. But what I can do is I can break it down, break it down, break it down. So what I'm going to do here is I'm going to say, well, with that 20, excuse me, with that 27, it is 9 times 3. And I'm going to say, okay, now hold on a second, because I know the square root of 9, that's 3. 3 times 3 will give me 9. So I'm going to take that square root out, and like we had discussed before, when I take that 3 out from the square root of 9, when I take the 3, how do I combine it with that 5? This is one great big multiplication problem. Yes, there's a subtraction here, but this is all multiplication. So when I take that 3 out and combine it with that 5, I'm going to do 5 times that 3, and 5 times that 3 will give me 15. So I'll have 15 square roots of 3. So now they are like radicals. And so I have 15 of these square roots of 3. I'm taking out 4 of them. How many of them are left? I now have 11 of those square roots of 3. So once again, I'm going to retain the radicals that are alike, and I'm going to work the coefficients. One more. Okay, so we have 7 of these square roots of 44x minus 8 of these square roots of 99x. But see, in my pile here, I don't have square root of 99x's. I have square root of 44x's. So here again, I'm going to need to simplify those radicals in order to be able to work with them. So that 44... can you think of a number that you can multiply by itself to create a 44? Nope. But I do know that 44 is 4 times 11. And how about, can you think of a number that you can multiply by itself to create a 99? Nope. But I do know that 99 is 9 times 11. Here again, why is this helpful? Because I know that the square root of 4 is 2. I'm going to take that out and combine it with the 7. I know that the square root of 9 is 3. I'm going to take that out and combine it with the 8. And just like before, how is this 2 going to combine with the 7? Great big multiplication problem here. Great big multiplication problem here. Yes, they are being subtracted. But when I take that 2 out here, it will be 7 times that 2. The 11 and the x will be underneath. When I take the 3 out here, it will be 8 times 3. And again, the 11 and the x will be underneath. 7 times 2 is 14, and 8 times 3 is 24, but the beauty is, hey, I have like radicals now, so I can combine them up. Because I have 14 of them minus 24 of them, so I'm going to work those coefficients, and 14 minus 24 is a negative 10, and I have negative 10 of them. I'm going to retain what's making them alike. The radicals are alike now, and I'm going to keep that because I worked awfully hard to get it and work those coefficients. So I hope that helps with the idea of being able to combine up like radicals. Just like terms, you can only combine them up when they are like terms, and that means the radicals have to be the same. But when they are the same, work those coefficients and retain what's making them alike. It's the radicals that are making them alike. I hope that helps. Have a great day.